Well, so today, Moritz Epke, I'm from Hamburg, from the University of Hamburg, and also affiliated to the Max Planck Institute. Today's talk will be comprised out of two parts. The first part will be about overturning of mixed layer eddies in the North Atlantic. And the second part, thank you. And the second part is about the impact of tides and eddies on ocean energy spectra. So let's go into the first part. As a motivation, I put a satellite image, which you can see here on the right. And what you can see is that it's a satellite shot which shows the chlorophyll concentration in the ocean. And this also indicates a submesoscale phytoplankton bloom, a phytoplankton bloom, and that one indicates submesoscale activity or the activity of mixed layer eddies. But what are mixed layer eddies? Mixed layer eddies occur due to various instability mechanisms in the mixed layer. They are mainly ageostrophic. They tend to restratify the ocean. They tend to restratify ocean fronts, and thus they influence the SST and the RC exchange. However, mixed layer eddies act on kilometer scales, or so-called submesoscales, and cannot be resolved in climate models. Submesoscales we define to be smaller than the first baroclinic Rossby radius. So whenever ocean modelers arrive at the problem when they go subgrid scale, they typically employ parametrizations. And parametrizations often are derived from theory, and they're tested in other setups in various ways. However, it remains unclear how good these parametrizations capture the effect of submesoscale dynamics or mixed layer eddies. So that's the guiding research question for the first topic, for the first part. But let's go to our approach. So we also use an ICON model. ICON was introduced before by Zoe. Here we use it in a quite different setup. We have a global ocean model with realistic era 5 wind forcing. Era 5, for those who don't know, is a reanalysis product which is mainly fed by observational data. And our configuration is special in that sense that it uses a kind of telescoping grid. So we have a continuously refined grid towards the North Atlantic. So what you can see here is the lines of horizontal resolution, and within our focus region, we go beyond 600 meters horizontal resolution, which is unprecedented in that type of model. What I show here as an image is the Rossby number, here expressed by the relative vorticity over the planetary vorticity, and strong colors indicate strong ageostrophic circulation. But how good is our model? Let's first have a look at that. So what you can see here is a satellite image up here you can see a satellite image, a snapshot of the sea surface temperature from Moritz Aqua. Has a 5 kilometer resolution roughly. And we use that snapshot to determine the variability of the sea surface temperature. So here you can see a wave number spectra. And what you can see in comparison is the red line with satellite data. The blue line is our present model. And the green line is a typical 10-kilometer model. And the 10-kilometer model is a typical climate model, but let's say high-resolution climate model. So that's the highest they can do at the moment. So if we look at this, we can directly see that submesoscales are not only hard to simulate, they're also challenging to observe, because we can see that the observations end here at 5 kilometers, this is the Nagus you can see. So we hardly evaluate a broad range of the submesoscale band. So this might not be the most appropriate way. I have a more appropriate way for you later. But what we can get from here already is by resolving the smaller scales, we also improve the intermediates and the large scales in comparison, especially in comparison to a 10-kilometer model. So we get the variability right on that order, and that's what you can already see here. Maybe with the onset of the new SWOT mission, we soon have higher resolution satellite data to do better evaluation in that sense. But what do other people do? So we looked on, I was using a study of Uchida et al. From 2023, and he was comparing submesoscale resolving models. It's like that's kind of the top of the art, what you can get at the moment. And I extended this study by our own model to just see where we are. And what you can see here, our model is the blue line, and all the other colors are the other models. We don't need to go too much into detail. What you see here is the sea surface height frequency spectra. Thus, we don't have satellite images as comparison here, because we don't have such time series. And you can see that the other models range from 3 kilometer to 1 kilometer, so they're still a bit more coarse. And we agree well on intermediate scales, but what we can already see is that towards higher frequencies, we have a higher energy level. And I will show you later why this be important. So another view on how to evaluate if our model is able to resolve submesoscales is to look at the characteristic scale, which is crucial. And here we define that one to be the Rossby radius of the mixed layer. Put the equation here for you. So, and to figure out, and we want to ensure that our model resolves this characteristic scale properly. That's why we divide it by horizontal model resolution. And this is so the mixed layer depth is included here, that's H. So that's a crucial parameter. And you can see where we have deep mixed layers, we don't need such strong resolution. And we have 3 winter months simulated where we have strong submesoscale activity. And what you can see here is that in our research area, on our study area, our aspect between the Rossby radius and the horizontal model resolution is quite good. So it means that we go up to 25 times, we have 20 times higher resolution than the Rossby radius. And we state that this is sufficient to resolve the submesoscales. But let's get back to the mixed layer eddies. To study mixed layer eddies, it makes sense to look at the Richards number. The Richards number gives us a kind of mean stability characteristic. So I put the equation up here. Here we define it being the vertical buoyancy gradient, so the stratification times the vorticity squared over the lateral buoyancy gradient squared. So what you can see is a single front, and if we zoom in, we can already find, at low Richardson numbers, we find unstable single fronts, and we can see such a front here. So we can easily define in the long front and the cross front direction, and then we can say, let's average a long front, just to roughly have an idea. And before looking at the eddy, so to now look at the eddy fluxes, we apply Reynolds average decomposition. So we use a temporal mean of a week to get the fluctuation terms. And then the upper 2 figures, you can see the lateral eddy flux and the vertical eddy flux. And what you can see immediately, that they are strong where the isopycnals are tilted. So where the apycnals are tilted, we have strong eddy fluxes. And from there, we can also diagnose our overturning stream function, and which you can see here in this figure. So people who study this phenomena in ILS setups, they already would see now that this is quite similar to what they've been studied. So this agrees already very well, which is very satisfying. But let's go now to the parametrizations. Maybe I'd use another non-dimensional parameter, that's the scaled buoyancy gradient. M square is the lateral buoyancy gradient, as said before. And now we have 2 parametrizations which we evaluate. One by Stone, which is derived from linear stability analysis, and the other one by Fox-Kemper, which is derived from partial theory. And what you can see is that both parametrizations give us the lateral and the vertical eddy flux, and they are fed with a background state, which we said before that could be defined by the Richards number, but also by the mixed layer depth and the strength of the ocean front. So our alpha, you can understand as the strength of our ocean front. And we can also see that they differ in the dependence on the Richards number. So especially for the vertical eddy flux, the Stone parameterization has a Richards number dependence of -1/2, while Fox-Kemper says for the vertical flux, there's no dependence on the Richards number. So if we now think about our cross-section again, if we now apply a cross-frontal average, we arrive at profiles. And what you can see here is the stratification. So this is stratification of our ocean front. And you can already see we have very deep mixed layer here of roughly 400 meters, which is a very well mixed layer. And then we can also look at the other parameters. So we have the lateral buoyancy gradient, or the strength of our ocean front. So you can see it's quite strong at the surface and weakens a little bit towards the mixed layer base. Accordingly, we have our vertical buoyancy flux or vertical eddy flux being very strong in the middle of the mixed layer, and it ceases towards the top and the base of the mixed layer. This also agrees so far to ILS simulations. If we now look on the lateral flux, we find some deviations. In ILS setups, this would also cease towards the surface. Here we don't find that. We assume that is due to other superimposed processes, maybe due to windwork or other processes. Again, we can compute the overturning stream function. So if we now let's apply the parametrization. And what we feed into the parametrization is simply the vertically averaged n square and the vertically averaged m square. So that's temporally and spatially averaged. Thus, our ocean front is expressed by simply two numbers. Those ones we feed into the parametrization, and then we arrive at this phase. So in blue, we have the Fox-Kemper parameterization, in orange, the Stone parameterization. And what you can see is that you have a qualitative good agreement for the vertical eddy flux. So the shape is kind of there. There's a structure function describing that. We have larger differences in this upper part due to the before mentioned points. And we also find that the Stone parameterization does not offer a structure function. So we don't have a vertical profile, and thus it makes sense now to look on mean characteristics also of the parameterizations. So we find here that at the single front, we find that the parameterizations kind of do their job, at least in mean values. But this is a single front, and now fronts vary all over the realistic ocean, and characteristic numbers like the strength, stratification, everything changes. So let's have a look on multiple fronts. I hope you can see that. There's roughly 50 fronts selected here in the ocean, and they've been evaluated. They show very similar behavior, so we find different depths of mixed layer, but we still find the same overturning process. They have different strengths, but we kind of find the same process happening on these fronts. Now, in the next slide, each of these fronts becomes a single point. And the idea of this slide is now to compare the resolved eddy fluxes to the parameterized eddy fluxes. And each front is one point here. So again, for the same colors for the parameterizations. And the parameterization is fully described by the lateral and the vertical fluxes. So if we arrive on the diagonal, this would mean that the parameterization exactly predicts what we also diagnose in the model, just by taking the background state. And what you can see here immediately that it kind of works. Maybe not so good. We can see it's like we only have an order accuracy. Maybe one can say, yeah, this is still kind of okay-ish, considering that we have ocean fronts ranging over 2 orders of strengths, 3 orders of strengths. But you can see it's not really satisfying what we see here. So there's much of work to do in this field. Another feature which I wanted to show is that we can also look at eddies. And at eddies, we found in particular that the parameterizations don't work. They don't predict. So if we slice an eddy, we can also assume the eddy rim as a submesoscale ocean front. And we also find low Richards number at this ocean front. However, when we apply the parameterization, we see that the predictions are not adequate. So something is wrong here. It's another open question. So that's as much as I wanted to say about mixed layer eddies. Now I wanted to go to a newer topic. This is also placed in the South Atlantic. Zoe already mentioned an observation campaign which we had there. So from that observation campaign, we could use the data. And the data we have is from 2 moorings. We have ADCPs, and they give us a kind of, they give us horizontal velocity as a product. And we also have PIs, that's pressure inverted echo sounder. They give us, from there you can derive sea surface anomaly. So we have these 2 parameters, and now we have another set of experiments placed in the South Atlantic. So it's the same model configuration with this high resolution, but now the focus region is exactly placed around our mooring locations, so our observational data. So we use this observational data now to study the impact of tides and eddies on ocean energy spectra. And I can show you how far we went at this place. So what you can see here is the frequency spectra of the sea surface height. In red, you see observations. In gray, you can see the experimental one without tidal forcing, and in blue, the one with tidal forcing. The green one we should neglect for now. So what you can see is that for intermediate scales, but also for the submesoscale band, the near inertial peaks, the M2 tides, the diurnal tide, most of the peaks are very well represented by the model. Towards higher frequencies, we cannot say as much anymore because the noise of the model does not allow us to go deeper. Sorry, does not allow us to assess this deeper. So the noise is as high as the signal or higher as the signal, thus we cannot conclude much from this. But what we can also see is that the model run without tidal forcing is not only lacking the tidal peaks, but it's also having a lower energy level. So we can conclude that tidal forcing is crucial to get the variability levels right, or the energy levels right when we evaluate the variability. We can come to a similar conclusion if we look at the ADCP data, so looking at kinetic energy. We find a good representation of the submesoscale band. We find again that we have lower energy levels with the non-tidal, the model run without tidal forcing. And yes, then this is it to the observational data. I wanted to give you a short glance about what I'm looking at the moment. So if you look at this anticyclone over here, we can apply an eddy tracking algorithm so we can composite the time series of an eddy, which you can see here. And so we can follow a single eddy throughout the South Atlantic. And once we have such a time series, we can say, let's look into the spectra of that eddy. And what you can see here is the spectra from before. So that's what we now call the so-called background spectra. And we can see the eddy spectra on top of that. What you can see immediately is that the energy levels within the anticyclone are strongly enhanced, and that's over all frequencies. So that's there we will go deeper in. Another feature which I also wanted to show, because we have now this time series, we can also apply high-pass filtering. And if we apply high-pass filtering, we can see and look at this anticyclone. We can see wave patterns in the anticyclone, and this may be an indication for near-inertial waves, which are trapped in the anticyclone. If you look at cyclones, we don't find those patterns. That's not another topic where we want to go deeper in. But let's wrap up quickly. So what I showed you today is that we have a new type of model, the submesoscale telescope from ICON. It's a specific ICON configuration. We evaluated the variability of the model. We could show that overall we have good representation of the variability from large to submesoscales. We figured out that tidal forcing is crucial to improve the energy levels at high frequencies. Thus, this model enabled us to study mixed layer eddies, and we could observe mixed layer eddy overturning, which was also not given. And we could identify that we have recertification, thus it's an important process. Comparison with parametrization shows that parametrizations works with an order of accuracy, but not more, so there's room for improvement. And at the eddy rims, we have problems with the parametrizations. And as an outlook, I could show you that we will further have a new tool now to study submesoscale dynamics, interaction of submesoscale dynamics and tides, or even look into wave trapping. So thank you very much for your attention.
Thank you very much. We have time for one quick question.
Where's this the inertial peak, the inertial frequency?
It's the dashed line here.
Okay, so there's a peak. I was missing the peak.
Sorry?
I was missing the peak, the inertial peak, but you said it's there.
Yeah, it's in here. This is the average from the average latitude. The frequency, because it changes, because it crosses towards the northwest. I assume, I don't know for sure yet. I see these wave patterns, and I guess it's near inertial waves.
You can speculate, are they spontaneously generated or are they somehow forced?
I guess they are generated from the surface. And they're trapped, so I think it's not that something comes in, it's rather something does not go out, but it's speculation. And that's why we find them in the anticyclones. We also don't find them in the cyclones. And I think it's not a new phenomena. So if you look on the change due to the relative vorticity, you can find that the band where waves can exist is changed. So in the anticyclone we can see the waves, while in the cyclone we cannot.
Thank you, Moritz, again.